Hello, good morning and good evening to everybody joining the webinar today. Everybody in Singapore, actually. Always lovely to talk to you guys in Singapore. So thank you very much for joining this webinar today. This is the third webinar actually that we are doing in your area in Singapore. So if you have been lucky enough to join the other two, which was the EMC troubleshooting and then analyzing your scans. This one will take you a little bit further on the EMC journey, and Professor Arturo will be talking about the secrets of near-field debugging. But if this is the first time that you are joining the webinar, don't worry about it because Professor Arturo will cover lots of secrets of EMC debugging. So if you do have challenges in that area, then he will be able to help you with those. So thank you very much for joining. I am Cornell Roberts and I am the marketing manager for YIC Technologies based in the UK. So it's morning for me. So I just wanted to give you a brief outline on YIC Technologies. So with our products and solutions, we offer a very powerful way to look at your design. Our solutions will rapidly diagnose and identify the challenges you're facing with. So once you identified the challenges, it gives you the opportunity to then fix the challenge or problem, and you can retest, and that will show whether your product is ready for that EMC certification. So the solutions that we offer is there to help you to take the product to market much quicker than what you usually would. So that's in essence what we do. So we work with a partner network globally. So PCB GraphTech is our partner in Singapore. So if you have any queries or questions with regards to any of our solutions or what you see and hear here today, you can go through to their sales team and or to us, and we will be able to help you with anything. So I just now want to introduce you to Professor Arturo. So he's going to be leading today's presentation. He is YIC's technical advisor, and we work very closely with him in the EMC EMI field. So he's the founder of the HF Magic Lab, which is a specialized laboratory for design, diagnostics, troubleshooting, and he's also in the field of training the EMI, EMC, and the RF fields at the University of Zaragoza. So Arturo, without further ado, I'm going to hand over to you. Thank you very much for joining and doing the presentation for us today. If you would like to ask any questions after the webinar, please just pop them in the chat function and we will make sure to answer all your questions at the end of it. So thank you very much. And Arturo, I'll hand over to you now.
Okay, thank you, Cornel. Good morning, and good morning to all our friends from Singapore. So let's try to share the screen so we can start this one. So at this moment, I hope you see the first slide, the cover.
Yes, we do.
Thank you, Cornel.
Good.
Thank you. So thanks to our friends from PCB GraphTech, and I hope you will enjoy the webinar today. About scanning in the near field and trying to learn something about EMI and EMC from not a very complex theory point of view, but with a lot of demo circuits. Okay, so let's start with the first idea that is important from my point of view for EMI and EMC, especially for the people that is not familiar. Remember that you have a problem in EMI and EMC, you have always a culprit. That means a product or a circuit that is creating electromagnetic energy. You have the second part of the problem, that is the victim, is the circuit or the product that is receiving this electromagnetic energy. And finally, in the third position, you have the coupling mechanism or the coupling path. Okay, this is very important because usually this energy goes from the culprit to the victim through the air, through some kind of dielectric material, or through some kind of conductor, some kind of wires, cables, or chassis, or something like that. That is because we talk about conducted emissions and radiated emissions. Okay, so remember the first idea. We have the possibility to have culprits because we have circuits prepared to radiate or to create electromagnetic energy, like, for example, wireless communication systems. But remember that you have a lot of unintentional transmitters, any kind of home appliance, any kind of computer device, or any kind of product around you can be an aggressive circuit for other circuits. Okay, so the first idea is to identify the 3 points. If you try to solve an EMI or EMC problems by the typical methods of filtering or shielding, remember that you are trying to go to the coupling mechanism. That means you try to introduce something in the middle between the culprit and the victim. If the coupling is conducted, you will be using filters. And if the coupling is non-conducted, you will be using shields. Okay? This is a very effective way to solve problems. But remember, there is another important possibility to solve the problem, is to kill the culprit. I mean to stop the frequency generation. And to be able to solve the problem in this way, we need to locate where the energy is created in a circuit. So when you go to the laboratory for conducted or for radiated emissions, you will obtain typical results like this one. The result on the right, something like this, is a typical result coming from, for example, a digital device. You can identify this because if you go with your marker, with your spectrum analyzer, from peak to peak, you will be able to identify that the difference of frequency between the different peaks is something that is constant, usually related with some digital clock. No, we are in the narrow band situation because the resolution bandwidth of the spectrum analyzer is able to identify with resolution in frequency where the energy is exactly located. Typically, this problem is related with digital circuits, with circuits that are switching, like some kind of power converters, especially if you go to conducted emissions, blah, 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 blah. But the other possibility is to have something like this. This is what we call broadband. In broadband emissions, we typically identify some kind of, let me call, mountain. This mountain of energy is detected with some kind of resolution bandwidth that is usually fixed for EMC legal regulations. But it's very important to identify what is inside of this mountain. The origin of this kind of emission is typically related with some kind of ringing. You have some circuit that is switching with ringing, or for example, you are exciting some kind of resonance in your circuit and then this kind of ringing appears. Or the other possibility that is that you have some kind of parasitic oscillation. You are creating an unintended oscillator in your circuit. So sometimes it's very difficult to identify where this ringing or this parasitic oscillation is located. So we can go to some kind of techniques to identify the problem. So the general picture in a typical measurement system is something like this. Remember, you have your device under test, it's here, is in some kind of setup on top of the table, and some part of the energy is radiated to the environment. This energy that is radiated to the environment arrives to the antenna. In my figure, it's a typical log periodic antenna that is used for measuring electric fields. Why I am not measuring magnetic field? Typically, antennas for magnetic field are loops or have the shape of a loop. Is because in the far field, in this area here, the idea is that the ratio between the electric and the magnetic field is known and constant. And this is 377 ohms. If you have the electric field, you can calculate the magnetic field. And that is because this antenna is usually composed by rods. The rods are a typical antenna for electric field. And what you measure in the spectrum analyzer is a voltage. The voltage in the output of the antenna is proportional in some way to this electric field. So you need to know what we call the antenna factor to convert the volts you are receiving in the spectrum analyzer to the electric field that is in the antenna that the antenna is receiving. Okay, so what happens if you are here? If you are here, you are in the far field, and what you are receiving is a plane wave. That means electric and magnetic field are orthogonal, are 90 degrees related. So if you try to go close to the circuit that is creating the energy, if you go in that direction, you will start to go to the area that we call the near field. Like a general number to calculate where is this area, you can consider that this is something like lambda over 6. At a distance of lambda over 6, that means is related with the frequency of the signal, you will start to introduce your body in the near field. And in the near field, when you are here looking at the circuit, okay, the idea is that you are looking at the signals that are around the components, around the cables, around the enclosure of your circuit, but not all that energy is being radiated. That means that you can find energy or signals in the near field that are not present in the antenna. But the opposite is not true. I mean, if you detect a signal in the antenna, that signal is in the near field. And this is because in the near field is a good area to identify where is the origin of the signal that you are detecting in the antenna. Okay. So let's try to see how we can identify where this signal is. A typical possibility is to use a near-field probe. A near-field probe, magnetic or electric field, is something like what you see in the screen. No, a typical magnetic field probe is something like a small loop that you create between the inner conductor and the shield of coax cable, and an electric field probe is something like you put out of the shield a small piece of the inner conductor. It depending on the diameter of the loop or depending on the length of this small tip, you will have more resolution in location, or you will have more sensitivity to pick up more electrical magnetic field. Usually in EMI and EMC, we are interested many times in current. So when you are interested in current, you try to go to magnetic field loops. Okay, so this is the idea is that you will be able to identify the IDTs, change of current with time. And if you are interested in DVDTs, usually we work with electric field probes. And then you can scan, for example, PC boards, you can scan cables, or you can scan enclosures, trying to find where you have some kind of hot area, where you have common mode or differential mode currents in cables, or when you have some kind of leakage around the perimeter of your enclosure. So let's go to the laboratory and let's see how is the setup for today. Okay, so let's increase the size of the screen. So you can see here on top of the scanner, at this moment, forget about the scanner, and we will switch to the scanner later. And you can see in my two cameras, the possibility, let me see if we are able to see better the other screen this way with this kind of zoom. Okay, and let me remove this window from here. Okay, this way. Let's see, this way. I have 4 different PCBs. We are thinking about this is your product, is separated in different boards. I have this board here that is an RFID reader. Okay, so I am able to put here an RFID tag to read, for example, for an access control or for payment or something like that. I have a microcontroller board. It's connected with some kind of SPI bus with the reader, It's a digital bus. And for the microcontroller, I am using a small Arduino board. You can consider here your microcontroller. And I have an LCD display to show how the system is working. Additionally, I need to power the system. I am powering with this connector. And this connector is going through a cable to the other PC board where I have a buck converter. The buck converter is converting, I don't know, 20 volts to 12 volts. That is what I am using here for powering my microcontroller and the full system. No? So you have 4 different areas. They are separated, but perhaps in your design, they are in the same PCB, is the same. But I prefer to use the 4 different boards because we will be working with the cables additionally. So we will be able to scan what happened in the cables of my system. Okay, let's switch on the system. And you see that the display is on, okay? And then the system is waiting for a tag. I don't know if you can see clearly in the display with the camera, but the idea is that I am able to see here the message is waiting for a tag. So when I apply a tag here, okay, every time I apply a tag here, the display update the measurement. I don't know why it's not clear to see. Okay, no worry. Believe me, let me try to see this in a closer view. Okay, something like this. And you can see here that I am 4 reads. Let me try again so you can see it's working. It's 5, 6. Okay, every time I put the tag on top of the reader, I am reading and updating the display. Okay, so let's consider that we are interested in scanning with a near-field probe. Okay, let me try. How is the, okay, this way. Okay, in this way. The first thing to do is to consider how is the emissions from this circuit. You can see here in my lab this antenna. This is a small dipole, and I'm going to connect the output of the antenna to my oscilloscope. So let's see the window of the oscilloscope. Here, I am connecting the antenna channel number 1. So let me activate. So this is the output of the antenna. We can update the amplitude, for example, to 50 millivolts per division. This is the signal I have. Let me see more periods. This is the signal I have in my situation with the device on. Let me switch off. Okay, if I switch off, the signal is fully different. If I switch on, I have additional elements. Let me put here 100 millivolts per division this way. And let me see how is the spectrum of this signal. I mean, the output of the antenna in the frequency domain. Okay, so we go here, and then we can see how is the signal. Okay, it's off now. Yes, this way. Okay, so we are looking at from DC up to 200 megahertz. I see the output of the antenna. Let me switch off my product. When I switch off the product, this is the ambient noise. Because I am not in a semi-anechoic chamber or in a shielded room, I have not some kind of shielded system. Oh, turn off pixel background. I don't know what is this. Okay, so this is, you can see that this mountain here is around 100 megahertz. This is the FM broadcasting signals in my area, and I have additional signals here. If I go here to, for example, 100 millivolts per division, you can see what happened if I switch on my product. Okay, you can see that I have a very broadband emission. Okay, pop. I switch off, I switch on. So consider that I am creating a strong emission around the FM band. And I am very worried because this level is over the limits of my regulations, okay? This is the general setup. Let me try to scan where I can find this signal in my circuit. So for this purpose, I will be using my near-field probe. I will be using this near-field probe. Let's put the scope here, the scope window here. So this is the small loop I will be using for measuring magnetic field. If I go to the time domain window in my scope, I will activate the channel number 3 because it's the channel where I have my probe connected. And you can see that when the probe is close to the reader, I can see a strong signal. Let me put a vertical scale in plus minus 500 millivolts or something less, 200 millivolts. And let me see how is the signal with less time nanoseconds per division. You can see that it's a quasi-sinusoidal signal. Obviously, if we go to the frequency domain, this signal in the frequency domain will be something like a sinusoidal signal. You can see here the 13.56 megahertz signal from this RFID system. The RFID system is using one of the ISM band frequencies, is 13.56 megahertz. And obviously, because this is not a perfect sinusoidal signal, we can see the second harmonic and we can see the third harmonic. And additionally, I can see the mountain that is related with my problem of emission at 100 megahertz. No, if we go close to the microcontroller, when we go over the cables, you can see that I have a lot of emission at different harmonics that are related with this SPI communication bus. This is very important because if you have an SPI or I2C communication bus, a CAN bus or something like that, all this energy will be radiated very easily by your cables. And additionally, I have the activity around the cables. Around the microcontroller. Around the microcontroller, you can identify clearly this harmonic. This is 32 megahertz. Is one of the clocks of the Arduino with the different harmonics. I have other activity related with the digital communications, and I have a strong broadband emission in the 100 megahertz. This is the frequency I am worried about. Okay, so if I go to the cable, I can identify that in this cable there is a strong emission of the frequency of interest. Look at this, at the effect of the magnetic field orientation. If you rotate 90 degrees the probe, the signal you will be picking up will be lower. It's not reduced a lot because the cable of my probe is measuring to the signal. When I go to on top of the converter, I can identify that the signal is really big. So let's try to see the problem with the scanner. With the scanner, the idea is that instead of one near-field probe, we have a lot of probes. Really, I have more than 1,000 probes that are in some kind of flat surface with the possibility to measure the emissions of this system from 150 kilohertz up to 8 gigahertz. You can see here 50 kilohertz, but really this is a mistake. It's 150 kilohertz, okay, to 8 gigahertz. It's very sensitive, and the resolution for this system is around 7.5 millimeters. We will see at the end of the presentation how we can increase this resolution, okay? The idea is that because these very small loops are orientated in different positions, we can pick up currents in different orientations, and at the same time, we switch electronically from one loop to other loop in such a way that the scan is very fast. It's a quasi real-time picture of the activity of your PCB, like you will see later. No, really, there is 3 different possibilities for scanning. One possibility is the scanner I will be using today is the EM scanner. We have an additional possibility is the EM scan R. The possibility of the EM scan R is the possibility of measuring with high resolution. Remember, in the EM scanner, I will be able to do measurements at 7.5 millimeters, but with the EM scan R, this is very useful for measuring down to 60 microns in 8 different levels. I will explain this later. And finally, if you have the possibility or the need to scan in other situation, like for example, a very different H components or things like that, you can use the EM probe where you will be able to move the one probe, a handheld probe, automatically with a robotic arm. Okay, so you connect the scanner. This is what I have in my laboratory. Is the scanner is connected to my spectrum analyzer, and the spectrum analyzer and the scanner are connected to the computer, where I have the software that is called EM Viewer. Okay, so let's see what you will be able to do. This is what I am going to do. I am going to do a spectral scan. So the idea is that I am able to identify what frequencies are coming from the device under test, and you will be able to do the spatial scan. That means for one frequency or for several frequencies, you will be able to see where that energy is. This is what is really useful to understand how your design is working, and how, or for example, where is this hot area that is creating energy that is radiated. I will present today the interleaved scan. The interleaved scan is a very easy technique to use the scanner in two different measurements to obtain a better resolution in your measurements. So instead of the first scan, that is a very good clue, and you can work a lot with this image, we can go to the second image, where it is easier to identify the current. Let's go to the laboratory again. So let's start to scan the system. To scan the system, I will need to go to the software EM Viewer. Let's put the cameras in this position. Let's put the oscilloscope out of the screen, and let's go to the EM Viewer software. Okay, when the EM Viewer software starts, the first thing to do is to try to connect to the scanner and to the spectrum. Oh, my spectrum analyzer is off, sorry. Wait a second. It's trying to connect to the spectrum analyzer and to the scanner. The software is working with projects where you can create different nodes. The different nodes for the software are spectral nodes, spatial nodes, spectral spatial nodes, and I will show to you today the spectral comparison. This is very useful to remove the ambient noise from your real measurements sometimes. Let me see, because it's failing in connecting to the spectrum analyzer, but it is because it was starting. Yes, it's connected. So let's start with a spectral scan. What is a spectral scan? Is to take the full system or part of your system and to measure in some specific frequency range. For example, from 10 megahertz up to 300 megahertz. This is my frequency of interest. Why? Because I know I am radiating in 100 megahertz. Okay, so let's select the resolution bandwidth. Let's go to 120 kilohertz. Very small resolution bandwidth means slower sweep for the scanner or for the spectrum analyzer, really. But the idea is that with a smaller resolution bandwidth, you have more resolution in frequency. The idea of measuring peaks is to be able to identify from their measurements a number of peaks that are the most important. For example, with 2, you will be able to measure exactly the peaks for these 2 frequencies. And then we select the probes you are interested to activate in the scanner. Look at this. Perhaps you are not interested in scanning the full number of cells, because you are only interested in scanning, for example, the reader. So if you go to this window with doing click, you see that we switch from white or orange to the green color. That means what? This cell is being activated. So to be able to activate the cells, you can do this directly, manually, or we can try to have help from the overlay editor. So the idea of the overlay editor is that you can import pictures, drawings, or for example, Gerber files. You can create the Gerber file, for example, for the silk screen and the top traces in your design. And then you can put the board, in this case is my Arduino board, on top of the scanner, and then you apply, you say okay, and then here I can select what cells below the circuit I am interested in scanning. For the spectral scan, remember, it's not necessary to scan all the cells. We can select a number of cells in this kind of random process. So we are interested in finding what frequencies are coming for the device, not at this moment where these frequencies are located. In this way, it's easier to make the measurement in a fast way. You can activate amplitude adjustment. For example, if you are interested in very small signals, you can introduce an amplifier in the path to the spectrum analyzer, so the dynamic resolution will be increased and you will be able to measure in a better situation. I am not using one amplifier. Many times it's not necessary to introduce one amplifier. So this is the window for the spectral scan. And now we start measuring, okay? So we will see now that the frequencies coming from the Arduino board are the frequencies you see now in the screen. Start. The system is on. Okay, this is. You can see that I can identify here a frequency of 32 megahertz, a frequency of 64 megahertz, this frequency here. These frequencies are the 32 megahertz from the 2 clocks in my PC board and some of the harmonics. Look at this circle. This circle is because the software has detected they are the 2 most important peaks. Remember, I selected to measure 2 peaks. And this area here is the area of my emissions. The other harmonics, narrow bands, you can see here, are coming from the digital communications that are being processed by the Arduino board, okay? So the idea is, how is the ambient noise in my system? Okay, so we can repeat the measurement, but with the switch system off. I have switched off the device. I switch on again the scan process. I am measuring with the device under test off. And you will see the ambient noise in my laboratory at this moment. Okay, let's try to do this, blah, blah, blah. It's not very, this is the idea. So I am detecting a frequency at around 163 megahertz. Perhaps the signal is intermittent. And you can see here the mountain that is related with the FM band. Let me create something that we call a node, a spectral comparison. In the spectral comparison, what I can do is to introduce in this screen 2 different measurements from the spectral scan. Okay, so for example, let's put this window here, let's put this window here, and now for the reference view, let me drag the last measurement. This is the ambient noise, okay, with my device off, and let me put in the test view the results from the measurement with the device under test on. So this is DUT on, this is DUT off, this is the comparison. So we can try to remove in some way the ambient noise from my measurements, okay? In many, many situations, it's good to know only the test view, because usually before doing the measurement, you can measure how is the ambient noise, and you can identify if your signal is bigger or not. If not, another solution is to introduce the scanner and your circuit in a small shielded tent, and you can ask a YIC technology for this possibility, and then your measurement will be shielded from the environment if you are interested in very, very small signals. Okay, now we have finished the spectral test. But for example, I am interested in finding where is the 32 megahertz signal. What do? You go to the spectral scan and you select the spatial node. And in the spatial node, you can introduce here any frequency, or you can introduce some of the frequencies we have found. Okay, why is it 100? No, this one. From this scan data, I have detected 32 and 64 megahertz, the 2 frequencies with the circle. I'm going to select 32. So I will be interested in finding where is the signal in my PC board at this frequency. So I go here, I select known, and now I will be selecting the full number of cells below my PCB, okay? Not random cells. I am interested in all the cells below this PCB. So I apply and I repeat the experiment, the measurement. Remember, this is a fully different measurement. For this frequency, I am scanning the full area of the device under test. And then we will be able to identify where the energy is located. Let me make a zoom. And you can see here the area where the 32 megahertz clock is distributed. This is what is very, very useful, because in this way you can identify if the frequencies of some megahertz are going, for example, to some specific cable or connector, because this high frequency energy going to connectors is very dangerous. Your cables will radiate easily this energy. This is very well related with how you do the layout of the PCB and how you introduce decoupling capacitors in your integrated circuits, and, for example, where you introduce filters like, for example, ferrites or inductors and capacitors. You can see the picture in 3D, okay? So you can move in vertical scale where the energy is located. Really, what I have here is the clock, the main traces of the clock, and that is because I have more energy. This is very useful to identify. You have loops in your PCB, or you have slots in the ground plane that are creating some specific area that is hot for your purposes. Okay, so let's go now to scan another different area of my system. I am interested in the reader. So let's start a new spectral node, and let's go from 10 megahertz, because the frequency of my RFID system is 13.56 megahertz. I don't need to go up to 100 or 200 megahertz. Let's go to 50 megahertz, for example. And let's just select 120 kilohertz, and we can measure peaks. It's not necessary, but let's measure peaks. And we are going to scan with these probes. I am going to unselect the cells. We go to the overlay editor, and now I will be importing, instead of a silk screen or Gerber file, I'm going to import a picture. You can take a picture with your phone, and you can move, like you can see here, we can move let's go with the window. Okay, let's go with the window here. Let's try to show you here. Okay, you can see from my camera that the RFID reader is from column AE to column AL, and from row 6 to row 10. Okay, perhaps you cannot see in the camera. Yep, this one. Okay, it's like the game of the ships, no? AG6. Okay, so let's go to put a picture in AE and reduce the size of the picture, this AE, and we go to AL, and we go to the number 6, something like this. So to 10. This is the position more or less of my RFID reader. And now I need to select some kind of area. Let me select several cells inside of the system. We apply, accept, and we repeat the test. This is something similar what I do previously with my near-field probe. Remember, I was introducing here the RFID. Oh, my system is off, so this is nothing. So let's switch on the device, and I will repeat the measurements. Let me stop this one, and let me scan again. Sorry, but my device was off. Now I am expecting to measure from this device 13.56, perhaps the second harmonic, and perhaps some other energy. Look at this. The most important frequency is at 13.56 megahertz, obviously. And the other frequencies are slower. No, it's a very quasi-sinusoidal signal. So this is the peak that has selected. This is 13.56. This is the second frequency that has detected, is 40 megahertz. Okay, and now we can do a spatial scan for this frequency. No, for 13.56 megahertz, 120 kilohertz. Let me see where is the energy. this way. Okay, select cells, and I apply. Only for one frequency, so it will be really fast. Okay, and now I will introduce what is the interleaving scan. Okay, so let's continue here, and we can see here the result. Okay, this is the result. We can remove the overlay if we want. We can change the scale of colors, and we can introduce the overlay, or we can see the 3D view of this system. Okay, so you can see clearly that the energy is around the loop. No, it's not 100% clear, and that is because I will introduce now the interleaving scan. If you are interested in more details in some specific design, you can create, I'm going to create a different node, so it's not overwrite, and for this frequency of 13.56 megahertz. But now I will check here. Look at this interleaving scan. Let me select first the probes of interest for me. I am going to select these probes here and select cells, this one. Let me select this area bigger around the PCB, accept. And now, oh, sorry, I forgot to activate the interleaving scan. Let me see the message is you are going to enable an interleaved spatial scan. This is the idea to reduce the blind spot in the measurement system. The blind spot is because of the orientation of the loops in the different cells. No, so to avoid this blind spot, we will make two measurements. The first one is in this position. The second one is moving the device under test one row to the top. So let's start. The first thing to do is we start. And now the message is adverting that be careful, you are going to do an interleaving scan. You accept. So it's doing the first measurement. And when the first measurement is finished, the software tells me I am going to do the second scan. Move the PCB one row in your scanner. So we remove the PCB one row. This is very easy. Okay, something like this. And we repeat the measurement. And with the two measurements, the software is able to remove any kind of blind spot in the case you are exactly interested of a good result. Look at this. Okay, if you see clearly in the screen, you can see that this PCB, let me try to show you with the camera. Perhaps you can identify how the PCB is done with several traces. Is a square shape. You can see that this square shape with 1, 2, 3, and 4 turns. This is the loop. It's a PCB coil with 4 turns in the top layer and separated with less than 1 millimeter. No, so obviously, in a theoretical point of view, when you have a loop and you are creating magnetic field, the area in the center of the loop is the area of less magnetic field, because the magnetic field is concentrated close to the area where you have the current in the loop. So this is what you can see here. What you can see here is that, let me remove the overlay, you have the loop, and you can see this loop in 3D, okay? So you can see very clearly how the loop is located related with the, let me see here, view 3D, overlay, view 3D aquí in this way, okay? You can move, or we can locate where this area is located, okay? So it's very useful to identify exactly where you have this energy in your system. Now let's go to identify, for example, for our problem. Remember, we were failing at 100 megahertz. Let me scan the DC-DC converter. Obviously, you can consider sometimes with the scanner or with the near-field probes, you can consider that the problem is located in the Arduino board. For example, no, if you go here, no, in the spectral scan, okay, remember, this is the result when I was scanning the Arduino board. So when scanning the microcontroller board, you detect peaks, narrowband peaks from digital activity, and you detect this mountain, and you say, oh, the energy is created in the microcontroller board. Be careful. This is not true. The problem in this case, you need to scan the full system because the energy is really created in the DC-DC converter. This is the problem in this system. And I have seen this many, many times, no? So if we take this approach, let me see. So the DC-DC converter is creating the problem, and because the DC-DC converter is powering the microcontroller board, the energy that is created here goes through the cable to the Arduino board. And then you see the signals, the 100 megahertz signals in this digital system. That don't means that the signal was created here, no? So you need to scan the full system to be sure what you are doing. So let's go to the projects. Let me create a spectral spatial scan. That is fully different. What is a spectral spatial scan? Instead of scanning spectrally in a frequency range and then selecting one frequency to locate where this energy is in the PCB, I am going to scan the full number of cells for a full frequency range that you specify here. For example, I'm going to select from 10 megahertz to 250 megahertz in a resolution bandwidth of 120 kilohertz, and I am going to measure peaks. Okay, no, it's not. Yes, let's measure peaks. For example, 2 peaks. Now let's go to select the scan probes. For example, I'm going to take now the DC-DC converter. Obviously, you can take a picture of the full system and you can scan the full surface of the scanner. I'm not going to do that, but it's something that you can do easily. So you can see from my camera that the DC-DC converter is located between the the F column to the K column, and they are going from row 16 to row 24, more or less, really less, no? So it's F16 from F to the other orange column, and then we go to more or less this, no? This one, no, this one, okay, in this way, more or less, I am not going to have a lot of time. From my DC-DC converter, I am only using the top area because here I have 2 DC-DC converters. This is a 5 volts DC-DC converter. This is a 12 volts DC-DC converter. So it's not necessary to scan the full board. Let me select several cells around this area. And let me show you that the results for this scan give me information that the 100 megahertz signal is created in the DC-DC converter. Okay, it's finishing. Yes, this is the result. Look at this. It's scanning, okay, some areas. So I identify a lot of energy. If I am interested in the full picture, you need to specify the full number of cells. For example, these cells here. And you repeat the test. Okay, and now doing a zoom, you will be able to see how the scanner starts to go from cell to cell, to cover in each cell the full frequency range of interest. No? Okay, you can see that the red and the blue colors will start to be changed as we go inside of the PCB because the energy starts to be concentrated in the area of your PCB. Look at this, we can identify exactly the area where the energy is located. Typically, the area around the inductor and the switching device, okay? We can remove the overlay, so we can identify specifically the area of interest, okay? It's finished. We can see this in 3D, so you can identify the area where the energy is located. This can be useful to compare, for example, different inductors, or you can compare different switching devices, or you can compare 2 different layouts with or without ground plane below the components in your DC-DC converter. I don't know what you want to investigate, no? And with the spectral spatial scan, we can do something that is very useful, is to go to the user composite view in the frequency domain, and then we can go to the cells, and we can say, "Whap, this frequency, this cell, how is the spectrum of this cell?" And they say this one, and this cell, this one, and this cell, this one, and the opposite. If you have the full composite view, you can be interested in identifying where this energy is. You click here, and it's here. But this energy, where is this energy? This energy is here, no? If you have different sources, here I have only the 100 megahertz mountain, it's more difficult to show the powerful technique, no? But if you have different energies, digital, narrowband, broadband, from some kind of ringing, it's very useful to locate exactly where the energy is created. So in my opinion, when I have finished the analysis of my system, I have a hypothesis. The idea is that I consider that the problem is coming from the DC-DC converter, and that is because I am radiating to the environment. So let's go to the circuit, and let's go again to the oscilloscope. We put the oscilloscope in this way, here, and let's go here to the time domain. We are going to go to the second channel B. Let's put in auto, and let's see how the switch is working. Remember, if you try to measure any signal that is more than some kilohertz in your circuit, be careful about the pigtail of your probe. What I am going to do is to take a piece of wire, and we will be using this technique to minimize the possibility of creating the ringing in our probe. And with this technique, we go to the circuit and we connect the probe to ground and to the switching device. Okay, this way. So now we are measuring how is the switching activity in my device. Let's take here, I don't know, 5 volts peak to peak. Oh, sorry, 5 volts. No, this is too much. Let's go to, 1 volt peak to peak. So we can move this, no, this way, and then we can move this to the lower part of the screen, and let's switch with the V channel, okay, this way. And then we can try to analyze the signal. This is what is very important during your debugging process, no? You can see that my device is switching in this way, but the problem is this ringing. You can see that my device, okay, if we go to less time per division, we see this ringing. This is because what? In this net of the circuit, I have inductance, I have capacitance, both of them typically parasitic inductances and capacitances, and there is no losses. So I have an underdamped situation when I excite the resonant with this step voltage function. So remember that to be able to solve the problem, the idea is to consider that you have something like this. You have something like this. Let me draw here. And you are creating this ringing because you have inductance and capacitance. The typical solution for this is to introduce some kind of a snubber or to introduce some kind of ferrite. With the snubber or the ferrites, what you are trying to introduce is losses, especially with the ferrite. With the snubber, you can control to the DVDT. So reducing the DVDT, increasing reducing the DVDT, you can try to solve the problem, no? And the result of introducing the ferrite could be something like this. So this is a system that is damped, okay? And then when you solve the problem of this ringing, then your product will be able to radiate less energy, no? If not, you will need to go to the system and you will need to repeat the measurement in this way. We create a node spectral spatial from 10 megahertz up to 200 megahertz, 120 kilohertz, and then, oh, no. Let's go to the, yes, I think we can do this. And then instead of loading the PCBs, I can import the picture of the cable. Okay, this is the picture of the cable. And look at the screen. You can see that the cable is located in row 11. So it's in row 11 that goes to column 1, 2, 3, 4. 1, 2, 3, 4, something like that. Is located here, and we can do something like this. Shoop, something like this, if I am not wrong. More or less, I'm not going to dedicate a lot of time to a very exact position because I think you understand the idea. Okay, I hope this is correct. Now I select known and I select the area of the cable, select cells, apply, accept. So we repeat the analysis only with the cable. Remember, I am not interested in moving, in modifying the PCB or in introducing snappers or ferrites or something like that. So we are going to scan the area of the cable. Now the system is on, correct. We can remove the overlay. And you can see that in the area where I have the wire, I will have some kind of activity at this energy. This is the noise that is going from the DC-DC converter to the microcontroller board. You can scan the cable that is going to the power supply if you want, no? But you can see that they have some kind of red and green colors here. The idea is to repeat the test now, but with a ferrite. No? So if you go to select a ferrite, I'm going to use a Burth ferrite. I go to the data sheet, and you can see that at 100 megahertz, this ferrite is introducing around 200 ohms. They are losses for this energy. So let's go to introduce here this ferrite. So you take the prototype of ferrite. Let's show you the cameras. Okay, in this way. So you can see what I am doing. Okay, so I open the ferrite. Oops, sorry. Oops. I open the ferrite and I move the cable to introduce the ferrite in this position, for example, this position here, and then I fix again in position, and you can see the difference. Okay, now we will repeat the same measurement, but with the ferrite in place. Okay, and then we compare. This way, you will be able to see how is the reduction in decibels between with and without the ferrite or comparing two different ferrites. And if remember, if you reduce this current in this cable, I don't know, 10 dBs, what you will obtain is a reduction of 10 dBs in the electric field at the distance where you have the antenna, okay? You can see here that at this moment, the color looks like blue. Okay? The system is not able to go with the noise to the microcontroller board because the noise is finding the ferrite in the center of the cable. No, if you want to avoid the noise going out of the PCB, the best position for the ferrite is exactly in the position of the connector. So if you want to avoid the noise going out from the DC-DC converter to this element, the best position for this ferrite is exactly here. If you want to avoid the noise going from the DC-DC converter to the power supply cable, the best position is in this situation. No? So you can see here the new result. Let me call this open data. This is no ferrite, and let's call this with ferrite, So we can compare, no? And now to compare, what we do is to go to the scale option and we remove the auto scale option. For example, let's work with the scale from 0 to 24. From 0 to 24, this is the result. And with ferrite, we go to the scale option, 0 to 24, the same scale, okay? And this is the result. This is no ferrite and with ferrite, okay? Remember that because we are creating noise in 100 megahertz, there is some possibility to measure with the scanner the ambient noise coming from the environment, no? But you can see that additionally, comparing the amplitudes, the emissions have been reduced some dBs. I don't know. For example, in this frequency here, that is going to 23 dBs. This frequency is going here to, I don't know, to 23. Sorry, this frequency that is around 111, 23 dBs. 110, this one here more or less, is going to 6, no? From 23 to 6, we have reduced the amplitude of this signal around 20 dBs, 18 to 20 dBs. This is what you can experiment with your system. And finally, let me speak very fast about the higher resolution. The idea of the scanner with higher resolution is that we have the possibility of obtaining up to 8 levels of resolution. If you want more resolution, remember you will need more time for the scan. And the idea is that the scanner, additionally to the electronic switch of the different cells, has a very high precision movement of the scanner. And this high precision movement of the scanner gives you the possibility to obtain up to more than 4,000 times more number of points for the measurement. So we go from 7.5 millimeters to 0.06 millimeters. No, this is very useful. We have it in the slides. I suppose you will have access to these slides. But additionally, to be able to measure with precision how is exactly the current path or the activity in some board, this is very useful if your device is very small or in high density populated PCBs. No, for example, here in an integrated circuit, you are able to identify in what part of the integrated circuit you have a specific frequencies. No, or you can go in the next slide. You have the difference of scanning with 7.5 millimeters or scanning in the level 6. The level 6 is exactly 0.32 millimeters, no? So it is 0.2 millimeters of precision. So you can go exactly at what pins in the integrated circuit you have the activity. Very useful to identify or to study small systems, or like I was explaining, very high density and small PCBs. So that's all. So I hope you will have some question and I will be happy to answer.
Thank you very much, Arturo. That was really a good presentation. Really good, interesting about the interleaved scans. That was brilliant. So anybody have some questions for Professor Arturo? You can pop them in the chat room. There's nothing there at the moment, but or you can just unmute yourself and ask a question if you like.
No questions?
No, doesn't
No?
look like it. Great.
What's
Okay.
clear?
Everything was clear. Thank you very much, Arturo. As always, thank you to PCB GraphTech for arranging this presentation. We will share this recording with them. So if you would like the recording or want to go through it again, just get in touch with them and they will be able to send you the recording. So thank you very much. Have a good day or good evening, and we'll see you all very soon. Thank you very much.
Take
Bye-bye.
care. Bye-bye.